Hi, I'm Zhijian Liu, and I'm a third-year PhD student at MIT working with Professor Song Han. Today, Haotian and I are going to share with you some of our latest progress on AutoML for efficient 3D deep learning. The trend of AI is to become smaller, as we would like to deploy the AI algorithms not only to those powerful cloud hardware, but also to mobile devices and even tiny microcontrollers. This is also the case for 3D deep learning. To begin with, let's get familiar with the basic concepts of 3D deep learning. 3D data is collected by the LiDAR sensor and comes in the format of point cloud. The collected 3D point cloud is essentially a set of points, each of which is composed of x, y, z coordinates and the intensity. The irregular and sparse nature of the 3D point cloud raises huge challenges for us to efficiently process it. Recently, 3D deep learning has received increased attention due to its wide applications. It can be used in VR AR headsets to understand the indoor scene. For example, to segment where the floor is and where the chair is. It can also be used in the self-driving cars to detect the pedestrians, cyclists, and cars. All of these applications are usually deployed on the results-constrained hardwares. Otherwise, in VR or AR headsets, the users need to put on a backpack full of computers inside, which is, of course, very heavy. For the self-driving cars, we need to put a whole trunk of computers in order to meet the computation demand of the autonomous driving systems. In this type of constraint scenario, it is of critical importance to design efficient algorithms that do not consume that many computations. However, designing efficient neural architectures can be very challenging and time-consuming. Over the past few years, there have been many manually designed neural networks that achieve promising performance on the ImageNet benchmark, such as VGGNet, ResNet, and more recently, DenseNet. However, they all require human experts to carefully tune the architectural parameters, such as the channel numbers, the kernel sizes, and the network depths in order to achieve that good performance. To improve the productivity, many researchers have proposed to use machine learning to design machine learning models, which is also known as AutoML, or neural architecture search. AutoML has various applications, mostly on 2D computer vision. To name a few, it has been applied to image classification, object detection, video recognition, semantic segmentation, and image manipulation. Apart from computer vision, it has also been recently applied to natural language processing. For image classification, the pioneering work NASNet searches the architecture of both normal cell and reduction cell of the model and achieves much better performance than human design. However, in order to design this effective model, the search cost is almost prohibitive for most academia researchers. To tackle this, many researchers have proposed to efficiently search the efficient models. Among them, a recent effort called Once for All proposes to decouple the training and search process so that expensive training costs only need to be paid once and can be amortized by many network evaluations in the search stage. It achieves more than 80% of top-line accuracy on the ImageNet dataset with fewer than 600 million max, which outperforms the human design by a very large margin. It is also 2.6 times faster than the EfficientNet and 1.5 times faster than MobileNet v3 without loss of accuracy. Apart from image classification, AutoML has also been applied to object detection. For instance, DesNAS applies neural architecture search to explore the best backbone network for feature extraction. And NAS FPN uses AutoML to search the connecting patterns in the feature pyramid networks. Similar techniques have been applied to video understanding and also to compressing the generative adversarial networks. In GAN Compression paper, the researchers are able to compress cycle GAN by 21 times, pixel to pixel by 12 times, and Gao GAN by 9 times with negligible loss of accuracy. As there are many successful attempts on applying AutoML to various tasks, a natural question would be whether we can also apply AutoML to 3D deep learning. The answer is yes, but it is not trivial. First, there is no well-defined search space in 3D like the mobile net search space in 2D. There is almost no research on designing efficient 3D modules like the depthwise separable convolution in 2D. Second, we also need to design efficient search algorithm for 3D as the training time for 3D models is much longer. In this talk, we will tackle both issues by first providing a better 3D module and then designing a better search algorithm. Let's start with the upstream, which is the efficient 3D module design. Designing efficient module needs to take the hardware into consideration. On the one hand, an efficient module should have some small memory footprints because the memory operation is more than 20 times lower than the arithmetic operation. On the other hand, an efficient module should also avoid the random memory accesses as it is much slower than sequential access. Conventional voxel-based models are not scalable because the memory consumption grows cubically with the resolution. However, low resolutions will lead to significant information loss, which leads to a dilemma here. With a single Tang XP GPU, we can only afford a resolution of 64 by 64 by 64. In this case, more than 40% of information will be lost. In order to keep more than 90% of information, we then need to double the resolution to 128. But in that case, we need to at least 7 Titan XP GPUs, which is not practically affordable for most users. Another stream of models directly process the point cloud. To apply the convolution, these models need to first query the neighbors of each point. However, unlike the 2D image pixels, these neighbors do not lie contiguously on the memory, and therefore organizing them requires considerable random memory accesses. Also, as the relative positions of these neighbors are not fixed, these models have to compute the convolution kernels dynamically based on the offset, which is also very expensive. After analysis, we found that up to 80% of their runtime is wasted on structuring the sparse data rather than on the actual feature extraction. Intuitively, we can capture the overall structure and fine detail of an object or a scene separately. With this specialization in mind, we propose a new primitive called Point-Voxel convolution, or in short, PVConv. Specifically, we have a point-based branch that extracts the fine-grained individual point features to capture the details of an object or a scene. Without the convolution, the point-based branch is very efficient. We leave the convolution to the voxel-based branch where we convolve over the low-resolution voxel grids to extract the coarse-grained neighborhood information. As the voxel resolution is relatively low here, this voxel-based branch can also be implemented very fast. In short, PVConv combines the advantage of point-based models, which is the small memory footprint, and advantage of the voxel-based models, which is the regularity. To test the effectiveness of our module, we first manually design a model named PVCNN by stacking multiple PVConvs together. On 3D segmentation, our PVCNN achieves a much better accuracy latency and also accuracy memory trade-off. It is 2.7 times faster and consumes 1.5 times lower memory than the state-of-the-art PointCNN. It can also achieve real-time performance on lightweight edge devices, including just a nano, which only consumes the energy of a light bulb. On 3D indoor semantic segmentation, the improvement is even more significant. PVCNN++, which is built on 1.9++, outperforms PointCNN by roughly 7 times speedup. Compared with the previous fastest model, which is PointNet, our PVCNN is roughly 2 times faster. It is also more accurate. In the first example, you can see PointNet misclassified the desk as the chair while our model gives the correct prediction. On 3D object detection benchmark, the KITTI dataset, our PVCNN accelerates F.9++ by 1.8 times while improving the MAP by roughly 1%. Here's an example video where the upper and lower images contain the 2D and 3D bounding boxes, respectively. Here, our model has already finished, while the baseline is still slowly making progress. PVConv is good at modeling 3D small 3D object or small-scale indoor scenes. But as the voxel-based branch in PVConv is still constrained by the GPU memory, it can afford relatively low resolution in this branch, which is not sufficient for the large-scale outdoor scenes in autonomous driving. In such case, some small objects will only occupy very few points. For example, from the right figure, we can see that the pedestrians only occupy 4 to 5 points, which is not enough for the models to extract useful features. In order to solve this issue, we upgrade our previous design module to SPVconv that combines the best from PVConv and sparse convolution. Concretely, it replaces the volumetric convolution in the voxel-based branch with sparse convolution. We have also implemented a specialized library to accelerate the sparse convolution operations. With this modification, the voxel resolution can be scaled up to very large in order to extract the features for large outdoor scenes. We visualize the attention of the point-based branch, where the points with top 5% largest norm are highlighted. The point-based branch learns to focus on small objects on the road, such as pedestrians and cyclists. All of these are done without any supervision. These more instances are usually ignored by the sparse voxel-based branch, which puts only less than 10% of its attention on pedestrians, bicycles, and cyclists. With the efficient 3D module in hand, the next step is to design an efficient and also effective neural architecture.
Hello, this is Haotian Tang. I'm a PhD student from MIT supervised by Professor Song Han. Previously, Zhijian has already covered the first part of this talk, which is how we can design efficient 3D modules which constructs the design space for 3D AutoML. Here, I will continue to cover the second part of this talk, in which we will discuss how we can search efficient 3D architectures with the 3D NAS pipeline we proposed in ECCV 2020. Specifically, in the 3D NAS pipeline, we support searching for architectures with elastic number of channels and network depths. As is shown in this animation, notice that the elastic channel numbers is different from the previous methods in 2D, where we not only consider the middle channels to be variable, but also allow the input-output channels to be different. We will cover the details later. And also we support the different network depths. To achieve this, in 3D NAS, we decouple network training and architecture search. We first train a super network that supports fine-grained channel numbers and elastic network depths, and then search for the best subnetwork under efficiency constraints. So specifically, in the super network training, we use a weight sharing and uniform sampling technique to jointly optimize a large number of subnetworks with different number of channels in our design space simultaneously. Notice that for the uniform sampling technique, we have the distributed sampling technique, which we will describe later. We further support the elastic network depth via progressive depth shrinkage. Assuming the max number of network blocks per stage is 3, which we will later call depths in this talk, we will divide the super network training into 3 segments. So in the first segment, the depths of each stage can only be 3. In the second segment, we allow the depths of each stage to be sampled from 2 or 3 with 50% probability respectively. In the final segment, the number of blocks per stage can be 1, 2, or 3. They are also sampled from a uniform distribution. So in this case, after the super network was trained for 3 segments, we have a large number of subnetworks which have all the possible depth configurations. We then run evolutionary architecture search to find the best subnetwork under max constraint. Thanks to the super network trained with weight sharing and progressive depth shrinkage, we can directly grab the weights from the super network without retraining. This actually greatly saves the cost of 3D NAS. Typically, we found that the cost of training a single network to be 68 GPU hours. The cost of training the 3D NAS supernetwork is around 136 GPU hours. That is 2 times the cost of single network training. After the supernetwork is fully trained, it requires just 27 GPU hours to search for a new specialized model under efficiency constraint. Therefore, the marginal cost for 3D NAS is much lower than training a new model from scratch. So here, we're going to continue to cover some more design details for our 3D NAS pipeline. So the first design detail is that small kernel matters in the 3D NAS design space. As is pointed out by Cai et al. In Proxyless NAS, which is also a paper from our group previously, the larger 2D depth-wise convolution kernels can be more efficient than multiple smaller 2D convolution kernels. This is actually because large kernels can usually reduce the number of kernel costs and better utilize the hardware parallelism compared with small convolution kernels. So Cai et al. Also discovers that using hybrid kernel sizes in the network can be a good choice. For example, the Proxyless NAS nets tend to use larger kernel size when doing downsampling. However, AutoML for 3D is very different from 2D NAS. One important characteristic for 3D deep learning is that the 3D point cloud data is sparse, and we have to perform sparse orchestration to effectively process the 3D data. In our case, because we use the sparse convolution operation in our PVConv module that constructs the design space of 3D NAS, we have to construct the kernel map to perform sparse convolution. Specifically, the kernel map is a collection of 3 tuples consisting of the input point, output point, and the kernel. It serves as the rule book for the sparse convolution operation. With the kernel map, we can perform the convolution operation by in place adding the product of the input feature and the convolutional kernel to the corresponding output feature. So we can also summarize the computation of sparse convolution into a 2-stage pipeline. In the first stage, we construct the kernel map. And then for each point, input point, output point, kernel tuple in this kernel map, we first gather the input features, then multiply it with the kernel, and finally scatter it to the output position in the memory and perform the in-place addition. So as we can easily notice from the 2-stage pipeline, the scatter-gather is obviously the memory operation. The matrix multiplication is obviously the computation. So what about the kernel map construction? Here, we should notice that in real implementation, since the data is stored sparsely in the memory, we cannot directly infer a point's memory location given its coordinates. This is very different from 2D or the dense 3D case we met with in the Point-Voxel convolution. So in order to obtain such information so that we can later perform the in-place addition, we have to resort to 3D sparse hash map query, which has a complexity of OK to the power of 3 times n. This just indicates that when the kernel sizes grow, the complexity of hash map query can grow cubically. So we found that building the kernel map of 5 by 5 by 5 convolution is actually 4.6 times more expensive compared with building the kernel map for 3 by 3 by 3 convolution. This is actually because we have to query 125 positions for each output point in the kernel size equal to 5 case, where we have only have to query 27 positions for each point for the kernel size equal to 3 case. Furthermore, we also find that hybrid kernel size is definitely not a good design choice in 3D NAS. Using multiple kernel sizes means building kernel maps for multiple times. This actually ruins the kernel map reuse across the entire network stage where the resolution is not changed. And this further lifts the cost of kernel map construction to 5.6 times comparing with using only 3x3x3 sparse convolution. So notice that for the largest kernel map, the cost of constructing it with the kernel size equal to 3 is around like 10 milliseconds to 20 milliseconds. So imagine that if we are using the hybrid kernel sizes, this will increase the cost to over 100 milliseconds, which is not acceptable. Furthermore, on the computation side, assuming that we are operating on the dense voxel grids, then we can find that one 5x5x5 3D convolution requires 2.3 times max compared with two 3x3x3 3D convolutions. Even for the sparse voxel grids, we also find that the larger kernel is more expensive. So based on these observations, we conclude that using large kernels or hybrid kernel sizes in 3D NAS is suboptimal, and it is important to stick to small kernels. Here, we continue to justify our design choices in the 3D NAS pipeline. For example, fine-grained channel numbers is necessary. We first recap the difference between our 3D NAS channel design space and the conventional 2D NAS channel design space. So in 2D NAS, the input-output channels for each basic block is usually fixed. Conventional methods tend to search for the middle channels only, or they call expand ratios in previous literature. This is very likely because people usually start from very efficient models in the beginning into the AutoML, such as the mobile nets. Therefore, the 2D AutoML method do not need to support models with a large range of max or efficiency constraints. However, in 3D, we are facing a different situation. Our starting model, let's say the Minkowski net or our manually designed SPVCNN model constructed by the sparse Point-Voxel convolution is not very efficient. They can only run at 3 frames per second on an NVIDIA GTX 1080 Ti GPU. Therefore, we might need to support a max range of over 10 times in order to explore very efficient models that are around 3 times faster compared with the baseline models such as Minkowski nets and SPVCNN, so that it can run in a very close speed to the LiDAR acquisition frequency. So in this case, scaling the middle channel numbers only is definitely not enough. We therefore need to support the input-output channels of each block to be variable too. Besides, as is mentioned before, all the channel numbers to be selected from the continuous range with a stride of 4 for all the middle channels. This allows us to have more flexibility in the 3D NAS pipeline. We then explain the design details related to elastic network depths. To understand this, we start from a small example of scaling down the width of a small SPVCNN model with 7.5 G flops computation by 2 times. As the number of max reduces quadratically as the number of channels reduces, we see a 4 times max reduction after the channel shrinkage. However, despite the large difference in max of flops, the resulting model is just 1.1 times faster than the original model. This warns us that simply scaling down the channel numbers in the 3D NAS pipeline is not sufficient for us to obtain models with very low latency on real hardware. So actually another very big challenge for 3D neural architecture search pipeline is that the dataset we use is much smaller than the datasets used in 2D neural architecture search. For example, the largest available 3D semantic segmentation dataset, Semantic KITTI, contains around 19K training samples. However, in image recognition, the ImageNet dataset, which is usually used by 2D neural architecture search methods, contains over 1 million images, which is 67 times more than Semantic KITTI. Larger number of training samples will lead to larger training steps. For example, if the networks are trained for the same time on ImageNet and Semantic KITTI, we found that we are able to sample 85K architectures if we are training on the 2D case, which is ImageNet, and only 17K if we are training on the 3D case, which is Semantic KITTI. So in this case, existing 2D NAS methods, even if they sample the same subnetworks on different GPU workers, the super network can still be well trained, and sometimes we can call it balancedly trained. So we terminate this sampling strategy as synchronized sampling in the 2D neural architecture search. But actually for the 3D neural architecture search, we conclude that the synchronized sampling may not work because first of all, we have a much larger design space compared with the 2D NAS methods, right? We have the fine-grained channel numbers and also the elastic network depths. This is very different from the 2D NAS. The second part is that we have 4.7 times less number of architectures sampled. This is mentioned before. So in order to solve the shortages of the synchronized sampling, we propose a very simple yet effective solution called distributed sampling across GPUs. So actually, we still use the same uniform distribution on all GPUs. However, we do not fix the network architecture sampled on each GPU to be the same. So in this case, we will have the distributed sampling. We found in our experiments that after we train the super network with distributed sampling and run the evolutionary architecture search, we are capable of discovering consistently better neural architectures on the different max constraint from 20G max to 70G max. And the improvement over the synchronized sampling trained super network is around 1% in MIOU. So we believe that distributed sampling is very important in solving the sampling efficiency problem in super network training. Okay, I'm going to share our results of SPV-NAS on the 3D semantic segmentation tasks. So the SPV-NAS is actually the result of the PVConv module, which is previously introduced by Zhijian, and also the 3D NAS pipeline I just introduced. So our SPV-NAS model achieves new state-of-the-art performance on the Semantic KITTI leaderboard, which is the largest 3D point cloud semantic segmentation dataset. It is actually 29 times larger than ScaNet and 160 times larger than S3DIS datasets. The Semantic KITTI is also collected from real driving scenarios and provides point-level annotation for the video sequences. So this is actually very similar to real autonomous driving applications, which further makes this dataset very challenging and important. So we first show our results comparing our SPV-NAS with the previous state-of-the-art method Minkowski-net. We achieve 8 times max reduction and 3 times speed up over this previous state-of-the-art method while preserving higher accuracy. This allows our model to be more efficiently deployed on real self-driving cars. We also break down the improvements from our better module SPV-Conv and the AutoML pipeline 3D NAS. So as is shown in this trade-off curve, we found that if we replace the sparse convolution operation in the Minkowski-net by our sparse Point-Voxel convolution, this results in the SPV-CNN models. So we can find that the trade-off curve of Minkowski-net, which is in gray, is lifted to the green line in these figures. So this actually demonstrates that the designing efficient 3D modules is very important and is a cornerstone for the success of 3D AutoML methods. So we further apply the 3D NAS pipeline to boost the performance of SPV-CNN. This can lift the trade-off curve from the green line to the red line with up to 5 improvement under the same max constraint and 6% improvement under the same latency constraint. So our model is able to achieve like 63.6% IOU, higher than the performance of Minkowski net under the efficiency constraint of 15G max or 110 milliseconds on the GTX 1080 Ti GPU. So again, I'm going to emphasize that both a better module, SPVconv, which shapes the better design space for the 3D AutoML, and our AutoML pipeline 3D NAS improve the performance of Minkowski net equally. We further show the results of SPV NAS on small objects comparing with the Minkowski nets. So in general, our SPV NAS model can achieve 5% to 25% IOU improvement over Minkowski nets on these small objects. This will potentially make our SPV NAS much safer comparing with the Minkowski nets when deployed on real autonomous driving cars. We also compare our SPV NAS method with the projection-based methods. So these methods, they actually take the 3D point cloud as the input and then convert the point cloud representation to some kind of a 2D representation, such as the spherical projection or the polar projection. So these methods, they actually have their main computation in 2D and thus is well optimized. Even if our SPV NAS model, it has many kind of irregular operations, such as the scatter-gather operations and also kernel map construction we mentioned before, our SPV NAS is capable of run at comparable speed comparing with these well-optimized 2D computation-based methods. And furthermore, in terms of accuracy, we achieve like 3% MIOU to 10% MIOU improvement over all these very strong recent projection-based methods. And we also achieve up to 58 times smaller max and 46 times smaller number of parameters comparing with this projection-based methods, which further demonstrates the efficiency of our SPV NAS. We also visualize the predictions of our SPV NAS comparing with the Minkowski nets, and we observed that in the safety critical boundary regions and small objects, our SPV NAS model is capable of making less errors. Here, we present a live demo comparing our SPV NAS against the previous state-of-the-art Minkowski net. As we have mentioned before, achieving higher accuracy, our SPV NAS runs 3 times faster than Minkowski net. We have to mention again that our SPV NAS is able to run at very close to the real time, which is the LiDAR acquisition frequency, 10 FPS. Actually, our throughput is 9.1 frames per second. And you can see from this slide that our SPV NAS has already finished the prediction on the given sequence. However, the Minkowski net is still slowly making its progress. We further compare our SPV NAS with these projection-based darknet models in a real-time demo. So we notice that SPV NAS can achieve over 10% IOU improvement with 46 times model size reduction and 42 times computation reduction. Our model also runs at 11.2 frames per second, which is even faster than the frequency of the LiDAR sensors and also faster than well-optimized 2D projection-based methods. So this actually demonstrates that our SPV NAS model is not only accurate, but also very fast. In terms of accuracy, I can also point out that our SPV NAS achieves MIOU of 60.3, which is even higher than the KPConv method, a very strong 3D deep learning baseline, which is proposed in ECCV 2019. We further show the comparison between evolutionary architecture search and random search in this slide. As is shown in the left part of the slide, we plot the best holdout validation IOU obtained by evolutionary architecture search and random search throughout the searching pipeline. We can see that the evolutionary architecture search has significantly better sampling efficiency compared with the random search. The best model we found at the 20th iteration performs 4% better in terms of MIOU on the holdout validation set compared with the best model we found at the first iteration. However, for the random search, the best model we found is at last is even worse than the best model obtained in the second iteration. This is mainly because we have a very large design space which random search cannot efficiently explore. On the right part of this slide, we also plot the MIOU obtained on the real validation set after retraining the architecture found by the evolutionary architecture search and also the random search. We found that the networks found by the random search has very large variation in terms of the final performance on the validation set, but they are uniformly lower than our SPV-NAS model obtained from evolutionary architecture search. So we can safely conclude that evolutionary search discovers better model compared with the random search. We also visualize the encoder-decoder computation ratio of Minkowski net and our searched SPV-NAS models. Interestingly, we found that the original Minkowski net is extremely imbalanced in terms of the encoder-decoder computation. Over 3/4 of the computation is concentrated on the decoder, and in fact, most of them are on the last decoder stage. In SPV-NAS, however, the evolutionary architecture search pipeline learns to balance the computation between the encoder and the decoder to achieve better accuracy efficiency trade-off. Especially in SPV-NAS under small max constraint, like 20G max, relatively higher ratio of computation is put on the encoder, like 50%. So notice that with the uniform channel scaling, we cannot optimize the computation ratio between the encoder and the decoder. It is also very hard to achieve this with random sampling due to the extremely large design space. We believe that the balanced encoder-decoder computation ratio can at least partly explain the better performance of SPV-NAS compared with Minkowski nets and our manually designed SPVCN models built from sparse point-voxel convolution. So we finally visualize the results of 3D object detection where our SPVCNN achieves more accurate predictions in crowded scenes with many small objects compared with the second method, which is also built from the Minkowski nets. So we notice that the second method can make some missing predictions or duplicate predictions in the crowded scenes, while our SPVCNN avoids these mistakes. So in this part, we further demonstrate again that the effective 3D module design is very important. It's the cornerstone of the success of 3D AutoML methods. In summary, in this talk, we covered the whole design details of our SPV-NAS, a combination of SPVconv, which is introduced by Zhijian previously, and the 3D NAS pipeline I just talked about. The SPVconv module can efficiently model small objects in large-scale 3D scenes, and thus set up a very good design space for 3D AutoML. To efficiently and effectively explore this design space built up with SPVconv, we use the 3D NAS method to automatically search for the best performing models under efficiency constraints. We achieve 3 times speed up and 8 times computation reduction compared with the previous state-of-the-art Minkowski nets. As we mentioned previously, our SPV-NAS method also achieves new state-of-the-art results on the challenging Semantic KITTI leaderboard. On the left part of this slide, we show the official Semantic KITTI leaderboard for the published methods. Our method is actually ranking #1 with very large advantage over all other methods. We also show on the right part of this slide that our SPV NAS is still ranking #1 among all test entries on the real-time leaderboard. We believe our SPV NAS can have very important real-world impact, especially when 3D sensors start to become more and more popular. For example, Apple just announced that the new iPad Pro 2020 will be equipped with LiDAR scanners. So in the future, the acquisition of LiDAR data can be very easy, and there will be growing desire for efficient LiDAR processing algorithms, such as our SPV NAS. Also, the autonomous driving technology is quickly developing, where the LiDAR data perception is very important. We believe that our work also have the potential of being deployed on real autonomous driving cars to make it drive safely. Our work has already been covered by MIT News in early August for succeeding in shrinking the 3D deep learning's carbon footprint by making it more efficient. We will continue to make efforts on green AI and tiny AI for efficient 3D perception in the future. Okay, thanks for your attention and interest in our SPV NAS work at ECCV 2020. You are also welcome to check our other projects of our lab related to TinyML and efficient AI from the GitHub YouTube pages presented on this slide and also the website of Professor Song Han.